Okay. All right. Thank you for joining. So I'm presenting today some enhancements that we did to the code. As you noticed, Stefan presented on parallel I/O, which is almost towards the final step. But the question is that how are we doing right now? And that's the question of this presentation, particularly from start to Stefan's presentation. So you'll notice that it says understanding BIT1 particle in the cell simulation performance. And that's the idea of this presentation. When you run that Slurm script, the question is it faster or not? David asked the question regarding the GPU porting, which I'll cover tomorrow. And then there's this weak scaling question that I'll also cover tomorrow. But the question is, are we doing well, right? Is the physics correct? Perfect. But is it working faster? Is it getting the results that we want in time? So, okay. Let's continue to start. So I'll give you a motivation first, so to give you an idea of what's happening. I'll give you a background. Most of the background will be already relevant to you, so you already know all of this information. If anyone is online, this will be relevant for you to give you some background. And I'll give you an important question that needs to be answered, particularly for this presentation. And then the next presentation will be tomorrow, which is the GPU part. We'll talk about the environments, because that's quite important. You're using Vega and Carolina. So we'll talk about that as well. And then I'll give you some evaluations and some results. We'll talk about the tools, and then I'll give you some conclusions. And then we'll talk about some current work, which will extend tomorrow. So first, let's look at the motivation. This is relevant to you, so you already know most of this. So we have the next generation of magnetic fusion devices being developed in France, so ITER. There's this fusion reactor that's also being developed in this process, where it's giving us some wonderful power or trying to enhance this code and different processes. And then we have fusion energy, where you have two different processes. When they combined, they give you this heavier nucleus, and the bypass is energy, and that's what we want to enhance. And you notice the gentleman is holding the ball. What happens when you run that fusion code or fusion simulation, the energy is released and it goes down, but we want to enhance that. So that's why we're trying to get to an exascale in this case. So we want to generate more energy from fusion than invested in starting and in maintaining it. So at the end of the day, we don't want to lose anything at the end of the day in this case. So we have some supercomputers in Europe. A lot of this is happening in the US and in Asia. They have their supercomputers, but we're talking about Europe. So the first supercomputer in Europe was Vega, the one that you're having access to. And this fastest, I would say the pre-scale, is Lumi, which you don't have access to, which is the pre-exascale system. And you have these traditional simulation codes that you need to go, but there are several of them. There are lots of these supercomputers that you need to understand. And this was in 2021 and 2022, the fastest pre-exascale machine. And now we have Jupiter, which is the next step for BIT1, which we will be looking later, running this code after doing all of this work with the work of myself and Stefan and everyone in the team. We want to run this on Jupiter. And the question is, exascale codes, they need to have a certain status, and they have to have a certain format. They need to be efficient in parallelism and scalability. They also need to have efficient use of these complex memory hierarchy. For this particular presentation, when we go to GPU, it's going to be a completely different story, which we'll talk about tomorrow. And the last one, particularly for these presentation simulations, I/O, which Stefan mentioned, storage, retrieval, and analysis. So those nice little plots you're getting, the question is it efficient or not? Now, we need to investigate, we need to characterize, we need to understand the performance. So there's very, very important things we need to understand. There are 4 key things that we need to understand at this level. Tomorrow, we'll talk about some more stuff, which is very important. But now let's talk about the base. When David created this code and passed it to Stefan when he did his PhD, we need to identify the computational parts of the code, those functions. We need to analyze single node performance. So don't go to multiple nodes, just focus on one node. Then we need to evaluate MPI communication, load balancing, and scalability. There was a question about weak scaling. We need to understand this. And then we need to characterize the I/O. Even though I/O is only around 1%, 0%, and so, the question is it a bottleneck or not? Even that 1% can be a bottleneck. And we need to identify the performance and enhancements. So you see on the far right, nice simulation by David. David, this nice jet discharge, and it's simulating the edge part of the tokamak. And I got that from David. Thank you, David, for that. It was nice, a beautiful picture. Every presentation I present this nice slide. But when you look at this slide, you notice what's happening, right? You see some parts of this visualization is red and some parts are dark. So we have an imbalance somewhere. But the question is, how can we see it from an HPC machine, right? So David's team, if then I would say more production case, or a very complex case, like the magnetic fusion, it has more or less 17 particle species, millions and millions of interactions, 5,000 CPU core hours being used, and more or less 60 million CPU hours. And to get results, what David told us at the beginning in Plasma-PEPSC, in the project to get this code to exascale, it took him 6 months. That's a long time, just to get results. Very long time. And the reason why that's very, very crucial for us is that you only allow 24 hours on an HPC machine. So you have this question of checkpointing, restart, all of the stuff that Stefan mentioned today. So we have kind of a workflow to give you an idea of how we want to get there. So we're going to profile the original code. Don't change anything. We want to know what's going on, identify the gaps, and then optimize GPU porting, because now all the machines are using GPUs. And then when we get there, we need to check profile again and check the gaps and understand. But we want to move this 6 months to 2 weeks at the end of the day. And if we didn't get any gaps, we'll go directly to that scale, and there'll be a question of bit 2 and bit 3, which David will cover a little bit later, the future of the code. And if there are any issues or gaps that we need to find out, we'll go back to optimization again. And then we will basically go back to the present state. But currently, this is where we are now for this presentation, because tomorrow will be a different story, because we're talking about GPUs. So let me give you a little bit of background. David already gave this, so I'll be brief, a little bit brief, because it's more, this is already everyone in here is a bit person. So you have the particle and cell simulation code on the steps. You have the particle move, the weight in the grid field solver, and the weight to the grid to particle. But the key is this Monte Carlo collision that David mentioned. Nice, detailed. Originally came from Berkeley University. It has no fast, limited collisions, as David mentioned. And it has a natural solver with a cell-based index, particle index. And as David mentioned, the one that I'm very interested in talking about is the last one, which is no limit in the size of the simulation, which is interesting for me as the computer scientist in this case. Because that input file that David showed and Stefan showed, once I know how to change the parameters, I can use any machine I want at the end of the day. But the question is it efficient or not? That again, under the state. So let's talk about bit 1 particularly. Bit 1 in this case is a 1D code, 3 vector space. In this case, we use 3 species with the electrons and ions and neutrons. C represents the cell index. So you have this particle at the index for the cell. And then you also have the index for the particle itself. So when the particle moves to another cell, we get to know exactly where it is, which is very, very useful for this code. One of the actual most famous part of this code. The domain composition schema is enabled, which is part of the code. The data layout, particle information stored in memory, as Stefan showed you the little file, which I'll talk about a little bit later in this presentation. And then MPI communication is non-blocking. So there's no issue in this case, right? And then you have these time steps, right? So David mentioned you have to have the efficient amount of time steps in order to get results. We have this incremental process with the PIC codes. In terms of OpenPMD, which Stefan mentioned, so to give you a little bit of background, Stefan is totally right. It's very, very useful. I recommend it 100%. So they have a kind of structure. So there's the read and write, or in other words, you can say it's the producers and consumers in this case. So if you notice I highlighted the one in orange, it's because that's the one that's very, very useful for large runs, as Stefan mentioned. It's prioritizing I/O efficiency. And this came directly from the IDEOS team, and also is all around in their documentation as well. But OpenPMD's standard files are formatted in such a way for efficient storing and exchanging of data at the end of the day. So you notice when you run that file, that simulation, you basically will have so many files. It's because this different workflows that we'll talk about a little bit later. But for now, this is the structure, the OpenPMD structure, to give you an idea. The backends, you can see there are many different backends. The IDEOS 2, which is the BP4, and then the SST, which is the sustainable standard storage transport that Stefan mentioned. Staging standard transport, my apologies. All right, so let me give you a question now. All right, let's talk about this question. So how can we efficiently handle massive plasma simulation data on current extreme exascale systems? That's a very, very loaded question. Well, we need to know, we need to avoid some stuff, and then we need to know some stuff when it comes to CPU now. We're not talking about GPUs, CPUs, right? First, you need to think about data transfer overhead. We need to avoid those. We need efficient data transfer methods. We have this thread synchronization issues that can happen, right? So if you're using OpenMP or any form, in this case, you have to think about the optimal thread synchronization strategy. Load balance, important balance that can happen, some problems. Workload balance and strategies that they think about. OpenPMD helped us a lot with this. And then you have inefficient memory access, which can be a big problem, right? Cache hits, it can be a tremendous problem for you. We have to think about the optimal memory access pattern at the end of the day. So let's look at the environments that we used. So firstly, we had to try to figure out like how we're going to help David with this code, get it to exascale. So you can see there are 3 unique, distinct machines. Green Dog is a workstation at KTH, and we have administrative privileges, and I'll tell you why we use that one. And we have something called another machine called NJ, which is an HPC system that had 2 GPUs on it, where we started our work. And then we had Dardell, which is one, basically, I would say the little sister of Lumi at KTH, which is one of the very famous machines at the university. But I want to highlight Green Dog. Every one of you have a laptop, and you run the simulation. The reason why we use that is because on an HPC machine, we don't have administrative privileges. And in order to understand what's going on with the code, we need to first check this that you are doing currently right now. So we need to check that first and then go to HPC machine. So it's a staging process. Remember I said, before we go to exascale, large amount of machines stay on one node and then improve. And then, oh, it's wonderful. Now you can go So in this case, we need to think about a laptop case, workstation, what's going on in this case. And you notice I highlight some things, memory, cache, all of these things. We need to study this. In terms of OpenPMD and the sustainable staging transport backend, we use the machines because now we've already done all the work. Discoverer, which has now a CPU, a GPU now in partition. And then you have Vega, and you have Dardel. We need to use this and these kind of stuff here. And all of these machines are distinct. So you have IBM, you have AMD mixing up, and so on and so forth. You have AMD GPUs, you also have NVIDIA GPUs. So the idea is to have multiple machines to understand what's going on. So when David decides to go and use a machine, he now has an idea moving forward for this case. So in terms of the workload, Stefan mentioned this to you. He showed you the files when he run ls on the screen, and he showed you, and you look at all those files. But what is actually happening in the back? Actually, this screen right here, this little plot. Every node aggregates the data, all those files. So if you write 128 MPI ranks on that Slurm script you write, you would have gotten 128 of those files and more, as David said, depending on the parameter you use, 0, 1 in terms of diagnostics. So we didn't want that. So I want a case where if I'm going to use 100 nodes, well, that's 100 times 128. But we don't want that. We just want 100 files because we want to improve I/O at the end of the day. Okay. And as Stefan mentioned, there's a little file called with the BP4 at the end, and you can enable also profiling JSON file. He opened it and showed you this kind of information, but this is basically what it means. It aggregates all the MPI ranks information, this kind of workflow. So I believe you might know this information. If not, we use two different test cases. So we use the neutral, the ionization case, where all the species where it goes in the system, they interact with the deuterium gas, and then they cause this ionization, and then the neutrals decrease due to this ionization process, which is the simple case. And then you have the complex case, which the sheet one that David loves to talk about, which one, and yeah, we will start to think about this as well. You will notice something very interesting here. And before I tell you that, with the sheet case, you have the electrons and ions, they combine with each other and transform into neutrals. So you have, and then you have this kind of sheath or against the front walls. But you'll notice something on the screen. Minimum HPC system at below is 1 node for the ionization test, and then it's 5 nodes for this sheath case. And that's because that's how much memory and how much process storage is taking. And that's because you see total number of particles, which is billion, 2.2 billion, and then cells that are 3 million cells. And then on the neutral case, you also notice that there are no electrical and magnetic fields. Okay, so it's basic case we use. For the BP4 and SST backend, we use the neutral case, the ionization, because we wanted to start off with something and then go to the big complex case. Because remember I told you I just need the input file, and then I can send it on any machine in this case. But you see on the far right, a little evolution as Stefan plotted on the screen. After 5,000 steps, you have this kind of plot, and depending on what you select in the Python script, you can make a visualization of the evolution, time evolution of the number of simulating particles in this case. So you have CPU on the y-axis, x-axis is the simulation of particles, and the z is time. So it's a time, so it's going through time, all right? So let's look at the interesting part. So you got a little bit of background, you got the information. Now let's look at some evaluation and results. Let's look at the very, very interesting part. So firstly, we're going to start with the original BIT1 code, the one that you have on your laptops. All right, so that's a nice little plot in 2D and then the one in 3D, depending on what you enable. So firstly, you have to select some tools, right? And each of those tools need to be assigned to a question, and this is recommended. You don't just take a tool from a HPC machine and just run it. You need a question behind it. And each of those questions give you an answer, and that answer is a plot. And that plot gives you some information. And then you need to know what to do next after that. All right, so we need to know how to leverage HPC profiling and tracing tools to understand how to make our situation better. So firstly, let's talk about two tools. The first one is gprof and perf. You're very, very familiar with very, very popular tools. First one is gprof. It's an open source profiling tool. It gathers the execution time and it reports those frequent functions from the processor. And you can see on below, there's these nice images here, and you can see how fast exactly the functions are happening in your code. So when you run that Slim script, it tells you exactly which one is faster. When it's red, it's particularly very, taking very long. And then when it's around blue, it's pretty okay. Next is perf, very popular tool. Very useful in HPC. It's a profiling tool. It gathers the hardware performance counters and events, and it's mostly used on Linux machines, depending on what kind of machine you have, and you can use this. So below you see like a cache test. So we want to understand the cache hits, and then we want to be able to understand the events, what's going on with the code, how it's operating, right? Just don't run the simulation. How it's going to happen. So firstly, let's look at gprof. So what do we get when we use this tool? Well, first, right away, we understand three very important functions. The RJ function, which is the particle arranger within the appropriate cells. Then we have the mover. And then we have the binary collision operator, which is where you have this Monte Carlo collisions happening. But what do we notice in the plot? The orange one, which the ionization case, 75%, that RJ is taking very long to do its work. And the next person is the mover, right? So that's our automatic best case to make this code faster. So focus on the RJ and focus on the mover. That means that if I optimize those two functions, I would automatically speed up my code. That's the automatic case. Then what we noticed when we use perf, we said, okay, what about memory usage and cache hits? So if you notice on the screen, you see baseline, you see 10%, 20%, and cache hit. So we can see the cache hit is a script that gives us exactly very excellent performance and using the cache. So you have the different levels, the 1, 2, and 3. But what do we notice right away on the left of that plot? BIT1 has very good, nice low level, the L1 cache, but it's terrible on the level 3. Right? And the reason why we notice that, we see that, is because when we went ahead and reduced problem size, we noticed that it started to reduce. So every time you run that simulation, and if you use multiple number of CPUs, the data is being split, as David mentioned. Yeah.
Are you recording?
No. Yes. Yes, it's recorded. Yes, it's up there.
Oh.
Yes.
Sorry.
No worries. So yes, and then the baseline hindering the performance of the code. And when I reduce the problem size, just 10%, you see it's went right away to yellow. That means as I use more different resources, my data is being split, is being reduced. So I assume, and this just automatically, I haven't run the simulation yet, I assume if I use exascale, it's going to be very, very small data, right? But the question is the GPU be able to handle that? Well, we'll talk about that tomorrow, right? Okay, so let's move on. So what do we observe first? RJ, the sorting function, dominates. The current BIT1 setup didn't have any GPUs right away. And we notice that we can have a high bandwidth memory integration if we go ahead and enhance this code, particularly. And what this second observation we noticed was that the performance is linked to the problem size and effective use of the level 3, right? Cache utilization. And then the serial BIT1, which we know because Stefan presented earlier, runs and shows significant memory-bound behavior. Let's look at some other tools now. X-ray and Petaver and IPM. Well, X-ray and Petaver is in Barcelona supercomputers, if you're familiar with this. X-ray is instruments the code for parallel tracing, and then Petaver processes this to give you a little output. So all the outputs from X-ray, Petaver gives you the little visualization. And you can see below, I can run my 8 MPI ranks and get some runtime tracing, and then I can also get information on the MPI calls as well. And I can get these communication lines, then I can get to see how are they operating with each other. IPM, very, very useful tool synthesis developed in the US. It's a portable performance monitoring tool. It offers low overhead performance profiling tools in this case. And it focuses particularly on communication, computation, and I/O aspects. And it gives you very, very useful information, even buffer sizes, so many different stuff. You get this kind of web browser, and so on and so forth too. And it's very useful for very large runs. So firstly, what do we notice when we use X-ray and Petaver for communication pattern? We notice right away that the rank 0, right, the one below, is causing the other ranks to slow down. And the reason for this, it could be because of data gathering, transformation, with the ranks, synchronization. You have these plasma profiles that was mentioned earlier, a lot of calculations happening in terms of the physics, but the rank 0 is doing something, and then it's telling everyone to wait. So you can see those little communication lines, those little yellow ones. They are communicating to those ranks. When we do some long run, this is a strong scaling plot where the x-axis is the number of MPI processes, and then the y-axis is execution time. And this is the two different cases, because we wanted to originally write the code. We wanted to understand how the simple case against the complex case is running. And we noticed straight away we found a sweet spot automatically with this code. And right after you see 2,560 MPI ranks, you have the superlinear speed up happening right after that. Okay? And that means that every time I go on to multiple nodes or multiple MPI processes, the problem size, it starts to fit. You can see straight away that it scales pretty well. And it's because it's fitting in the L3 after you meet around 2,560 MPI ranks, which is around 20 nodes, or more or less in this case, at this test. Okay. What do we observe? We saw that the parallel BIT1, the communication shows some workload imbalance. So you have this parallel processes we wanted to understand using multiple nodes, MPI processes. And we saw that the slowest MPI rank causes local synchronization among the MPI, the neighbors of these. Go do some MPI wait call. And then the next thing we found out was the parallel performance showed some superlinear speed up in both cases, and more MPI processes led to a smaller problem size, and they fit in the cache. So that means if you decide you run this code on 50 nodes, it means that you have very, very small data per node and all those files, and it's going to be fast, as David mentioned. Yeah. IBM again, and Darshan. So IBM also, in addition to Mamito, is very famous code in famous tool in the US. It's not always talked about currently because they're stopped developing. It also gives you information on runtime in a text format, web reports, and it also gives you scalable and required information from source code when it's not modified. It's used a lot in HPC centers. So if you've never seen a HPC center, they use this a lot after they have a lot of papers now on this, using this tool, but they've stopped development, so you won't see it much now, but I use it a lot, very useful for an academic, the application development, debugging, and in academics. So if you like to publish papers, this is an excellent tool to help you to understand what's going on with the code. Darshan, now IO, yes, it's only 1%, 0% usage, but the question is, it's going to tell you those questions, I'll give you those answers, those questions that you don't see. So remember, there was a question I think David said after a certain point, there's crashing or something happening with the files. This will tell me why that's happening, right? What's going on. So this is a performance monitoring tool. It's designed for analyzing serial and parallel I/O workloads. It's used for identifying and tuning I/O behavior. So you see below there is two little plots. It gives you an estimation on performance of the I/O, and then also tells you the reads and writes. Get a little tracing to tell you what's going on with I/O. So first, let's look at IBM. So remember, David mentioned on the boundary ranks, this is a sheet case. That's the one you worry about. You don't worry about what's going on in the middle. But for HPC, we do need to know what's going on in the middle. For HPC case, for a computer scientist, I need to see everything, right? So right away, I noticed that those little boundary ranks that you're focusing on are the ones that are taking the longest. And that makes sense because you're spending time developing this. But then you notice that it's affecting the other ones, and it's telling you have these ranks are busy due to some processes. And then the memory usage also is being affected here, but it's balanced at some point. After a certain point, you can see when it reaches around 40, if you look at the little small box in the middle, you see it's after a certain point, it drops. It's because of something happening in the code after a certain point. All right, so it gives us very, very useful information. And then Darshan in terms of the I/O. So with the I/O part, when this plot shows you, this is also a strong scaling in this case, and it tells you the write bandwidth increases and then saturates. So this answers that question that David was talking about. After a certain point, the running code, it saturates after a certain point. All right, so you can see it peaks due to the problem size, and it drops due to metadata writing costs. So when you run that Slurm script with 128 MPI ranks, you should have gotten loads of files on your login node, right? And it's because of that, right? Which is a very, very big issue at the end of the day. So what did we observe? We saw that those two ranks at the end, those binary ranks, is 2 times longer than the others, and it's due to the MPI wait, so it's waiting. And the large MPI process causes self-synchronization due to parallel performance. And then we also notice that the BIT1 shows a serial I/O behavior, and the bandwidth rate rises after a certain point. It peaks because it reaches the sweet spot and drops due to the metadata costs that's happening with the code, particularly. So let's look at the BP4 and SST, the sustainable staging transport backend. So you see a nice plot. There's a plot we did with Stefan's support. So you can see it's showing the movie file, the first movie step, and then all the way to the end. So we get this kind of, so that means that at some point I can make kind of visualization, right? I can do some in-situ visualization at some point. But again, tools, right? Are we doing well or not? So when you get some tools again, we need to ask some questions. We need to see what's going on. And we need to think about different tools now, because now we're thinking about parallel I/O, right? So firstly, we have to go back to Darshan, right? Which is quite useful for us. We use Darshan to evaluate the I/O performance of BIT1 in terms of the write bandwidth. And we saw straight away that it peaks and then drops at some point due to this write cost. So firstly, what we saw, Stefan mentioned this earlier, that's the data in BIT1. After a certain point, it kind of has issues on the file system. But what you see on the screen is a strong scaling test, and we saw that there's a nice sweet spot. If we use 40 nodes, we achieve the very highest write throughput in most of those machines. So you have Dardell, Discover, and Vega. So we decide to go with Dardell because it's faster. We decide to use this. And then we notice when we use parallel I/O, we straight away saw that there's an excellent I/O stability has been achieved using the backend in this case. And it's due to tasks, the suitable tasks generated through the throughput and efficiency of the ADIOS2 library and the OpenPMD process as well. Excellent tools to use. Also, we decide to go ahead and understand, okay, well, I wonder, can I have multiple data files in my HPC machine? How do I know that's the most efficient when I just run and install ADIOS2 or OpenPMD in this case? Well, one node, one file, one DAT file tells us, wow, it's the most optimal because the file system is happy. It's not crying out for help because that's only one file as opposed to 128 in this case. Well, we saw that if I decide to use 400 aggregators, I'm faster than using that one file or 2 files per node. And it's only because Dardell has enabled the 2 different CPU processes enabled. And this tells us straight away that just using OpenPMD and ADIOS2 is not just the right way to do it. You need to think about what is the right amount of aggregators to use in this case, right? So I'm using 2 data files. It's a lot more efficient because it's parallel, right? We're using parallel I/O and we're using 2 data files. So I can write to 2 different files, and I get a lot more bandwidth in this case, or write throughput. But we notice when we decide, let's go to the normal BIT1, right? Let's run up to 200 nodes. Let's use all of the MPI ranks. And even in the most worst case, ADIOS2 and OpenPMD still outperforms the one file. So that means at the end of the day, it's still going to be a lot better to use OpenPMD and ADIOS2 in this case. So it's the right case for David's the code at the end of the day. all right? And then we notice straight away that it's most efficient in its extreme case, right, for BIT1. Another thing that we wanted to understand, okay, so what about data compression or with aggregation in this case? But again, we need to understand some more things. We need to think about why, what's happening. First, we saw that when we run this code, we saw there's an increasing number of files due to simulation. So when I went from 1 node all the way to 200 nodes, I see 5,106 files if I use 200 nodes. Whew. The file system is going to go crazy, right? So I decided to use OpenPMD and 200 nodes, 205 files, well, the extra files at the end of the day. So IO is perfect. And then we decide, I wonder if I use one aggregator, one file for 200 nodes. I don't want to use 200 files. We saw straight away, it helps us, the file system. But if you notice something, the average size file starts to increase. That makes sense because we're, I would say, aggregating everything in one file. But we're only focusing on improving the file system, right? Then next, we used compression, the BLAST compression, which ADIOS 2 has many different compression libraries. Once you enable it, once you can compile it correctly, we saw straight away that we can get 15%, which is pretty good. Not what we want to achieve, but we want, at least we've achieved this case. And we dropped a bit. So right now, with these parameters, we have improved the code in terms of storage efficiency. gprof, well, gprof tells us we started off with trying to understand the maximum performance, right, of BIT1. When we use ADIOS 2 and OpenPMD, right away, the RJ dropped by 10% without doing anything. No optimization at all. So just using OpenPMD and ADIOS 2, we just improved the code a little. Yeah, that's excellent. So now we can do some other things in this code. As Stefan mentioned, the write, the metadata dropped, and then the write dropped completely. So as Stefan mentioned, this is a normalized graph. So if I look at this, that would be all the way to the bottom, almost close to the BP4 word. But then if I check to see how fast it is, that's 17 seconds compared to 0.014 seconds in terms of the metadata, all those files. That's a lot of time being spent just writing files under this, right? And this is at 200 nodes, just giving you information there. So crate path. So if you're using a crate machine, it is very useful if you're using crate. So if you're going Lumi or Dada in this case. So crate path is another tool that you use, and it provides a lot of information about overall application performance. And it has like a little GUI, and it tells you a little bit of visualization and gives you some very useful information. And it's just completely like similar to Perf in a sense, but then it gives you a lot more. And it's really live while when the code is finished for post-processing. So we use CratePath to interpret the code first, and then we use Apprentice2 to interact with the performance analysis and visualization in this case. So you see the nice plot. I get to see energy usage. I get to see data movement. I have those in not enabled, so that's why no data, no information you see on the plot. And I can get load balancing as well. And I can get understanding of the whole function, those nice little green lines. So the very long means that's time, so you can take very long. So up and down in this case. So what do we see here? 1 node versus 100 nodes. So a small run versus a very large run. We saw straight away that MPI weight is around 25%. And then very, very large run, that's the BP4 backend. That's very good. We saw straight away that it reduced because the original code, there's a lot of MPI communication was increasing due to this and this saturation happening. And then when we don't have this I/O issue anymore, we now have some communication happening, and we saw straight away that MPI weight or synchronization, or that synchronization that we need, is being reduced a lot. And we didn't do anything, right? No optimization, no changes to the code, right? Automatically. IPM. Well, what does this tell us? Remember when we use IPM, this is for the ionization. Look at the boundary ranks compared to the other ranks. Up and down, all these things going on, right? In terms of memory usage, it's kind of stable, yeah? MPI weight is taking a lot of time, and that little kind of chart, the little the pie chart. But when we use OpenPMD, look what happened right away. Everything kind of stabilized. And then weight just completely drops to like third spot. And then we have this gather. Well, we know that's why is that, because we have the aggregation, right? And per node, all the MPI ranks are kind of funneling to one data file. So we expect that to be our problem, right? Dominating in this case. So we maybe need to optimize data gathering, yeah? And then we expect with the data gathering, there's some kind of receiving happening to happen, which is 19%. And the MPI weight, of course, will be there. So it suggests a little bit of efficiencies that need to happen because we didn't do anything to the code yet, right? We didn't do any optimization. Memory usage is important, especially for GPUs, because GPUs have a certain number of memory. So we need to remember this in the future for tomorrow. So we know straight away that it goes up to 33 gigs for this simulation. Yeah. Now let's look at the SST backend or the sustainable staging transport simulation. So you that BIT1 uses streaming, as Stefan mentioned. This what happens. I don't know if you've run it before. That's exactly what happens. You run the simulation, and right away you got this Python pops up, and you get all the time steps, all the different movie files happening right away, just on the fly, and you get to see the kind of evolution of using this case. But the question is, are we doing well? Let's see. So firstly, gprof, another tool, tells us right away that we used it to study the, try to get the maximum performance. Well, when we use SST backend, 50%. Didn't change anything. And automatically, RJ says, oh, that's nice. 50% improvement. Right away. And then when we use the mover, for the mover, it says, oh, that's nice. 15 or 49%. As opposed to the PP4, which started to increase because, that's expected because we have the checkpoint you're writing on the disk and so on and so forth. But we're not doing that anymore. We're streaming through memory, right? We're not writing on the disk. So we don't have to do that. So the mover and the RJ is happy. They're moving so pretty quick. Oh, that's very good, useful. But what do we notice on the other functions? Some of them start to increase, all right? That's because of MPI communication. That's pretty good because we know those functions, so we're using the accumulating function, MPI functions happening, and so on and so forth. And also the other as well, 18% is increasing. We expect that because we need to do some more optimization, right? At the end of the day. Darshan, well, we saw straight away that we need to check, compare the PP4 and the SST. Woo. Wow, we literally removed write completely from 1.04 seconds all the way to 0.000. So many zeros. We completely removed the write. Well, that's expected because we're streaming through memory, right? It's just an instruction. It's just telling the information and says passing information. And we expect the read to be a lot because we're reading. Write is completely gone. And then we expect a little bit of overhead to happen with the metadata because it needs to do a lot more aggregation. A lot more aggregation is happening with streaming through memory as well. Okay. IBM, very nice tool. Remember I told you that's very useful. Look at the difference from the before to now? Well, the first rank, rank 0, well, look at the time reduced completely, and it started to pass information to the others. So MPI received now is dominating because it's now passing information to the other ranks. As you saw in extra and petaverse, if I use extra and petaverse, I'll see some different plot, right? And then we notice also that the memory is also stable. We expect that. And then we have a nice little, if you look in the middle, that's a little kind of pie chart. It's kind of going stable. So it's MPI received, gather, broadcast, all reduced, and weights drops completely, yeah? So we can do some more improvement somewhere at the end of the day. So what this perf tells us? Well, perf gives us some interesting information. So I decided to say, okay, well, I wonder if I just use a nice strong scaling plot to see what's going on with the original code, BP4, and SST. So what do you see here? So on the x-axis, that's nodes, machines, in this case. And on the y-axis is execution time, yeah? So low is better, keep that in mind, because this is strong scaling, right? Weak scaling, we'll talk about this tomorrow. So firstly, keep in mind that the blue is baseline, which is the original BIT1. And then we saw straight away on one node when we use the original BIT1 BP4 backend and we just changed it to the SST, we saw, okay, we got a 7% improvement on one node. And then we start to use more MPI ranks because it's an MPI application, right? We want to have a lot more MPI processes happening. But at some point, the code saturates, right? Remember that sweet spot? 20 nodes? But the BP4 and the SSC says, no, I don't want to saturate. It starts to still improve after, at some point, 50 nodes. Then the SST says, oh, something is happening. We need to do something, right? So that means right away, I can use more machines, yeah? I can use more MPI, as David said, in this case. But we notice something happening here. When I start to go more, remember we're trying to go to exascale, 100 nodes in this case. Well, we saw straight away, if I continue with BIT1 originally, we will have a very, 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 very bad time. 128% increase. And then also the RDS2 and also the BP4 and SST starts to cry for help. So remember, we didn't do anything in this code. There's no optimization at all. So yes, it's decreasing, but it's improved. It's better than the original code, all right, in this case. So let's look at some conclusions and some work. So what did we find out? We found out that the problem size is impacted by this code, right? The scalability effect in the code, where there's some strong there's some superlinear speed up was revealed. The code is dependent upon the cache strategy. So the problem size is very important. So the more machines I use, problem size decrease. So I have to think when I use GPUs, for example, tomorrow when we talk about this, I have to think a little bit different how I work with the code. And as I mentioned, GPU porting is limited in this case. So there's a potential to improve the code. Data layout needs to change maybe. And then we think about the workload imbalance that happened in the code with the rank 0 in these large runs in this case. So as before, as I mentioned earlier, we have to stay here at this point, optimizing. Tomorrow we'll talk about optimization because we're going to talk about what we're going to do to the code and what we did to the code and how everything's going so well at the end of the day. And then for current work, we're currently right now optimizing the code. We have some different things we're going to do in terms of performance, portability, and productivity. There's some in-situ visualization Stefan mentioned that we are going to use. So you also have Power View as well. So you can actually aggregate all of the checkpoints, and then you could press play, and you could start to see what's going on with the code. moving forward at the end of the day. So we also has this nice visualization. And then we want to use some other features of OpenPMD has with ADIOS too, so things that we haven't touched yet, right? So there's also resilience and fault tolerance need to be think about. So remember, Stefan mentioned load balancing. In this case, we need to think about that because after 24 hours, you need to do a checkpoint restart, right? So we have to think about that, how we can understand this information. And just for give you a little visualization, as Stefan was giving you a little, let's look at visually what you would do and use this SST backend. So you're the BIT1 user, you're on your laptop or in machine, you connect all the way to Vega, and right away you need to run the Slurm script, or you can run srun in this case, and you should expect the simulation happening on in your login node, or in this case, preferably compute node, right? So SSH into the compute node and you'll be fine. And then you can actually use another feature that I learned when I was at supercomputing, where you can just use another node. So Stefan showed you on just one node or just run on his machine. You can use multiple nodes, just connect, and then run again. So I can have plots. So you have something called more or less visualization nodes, or in this case. So I'm not even affecting the code, so it's not blocking. And then right away, I can run the simulation, so on and so forth. So on one node, the code is running. On another compute node, I'm visualizing. Okay? But it's connecting to the same source code in this case. So it's a nice little feature that you can do in this case. All right. So I would like to thank you, everyone, for your time. And as I mentioned earlier, this is thanks to Plasma-PEPSC at the end of the day. Any questions?
Yeah, I have first of all, thank you very much, Jeremy, for presentations. I mean, for support and everything. I have a question. If you go to slide 54, please. I see that this weighting is quite asymmetric. So which case did you consider here?
So
for instance, this one too. I mean, even if you stop before, I mean, here, you see there's strong asymmetry. So it means that the rank, let's say later, so the largest rank are waiting for something. So first ranks are doing, and then what is the case? Is it a plasma sheath case, or it's?
This is the ionization test case.
And this is surprising.
Yeah, but that's what ADIOS 2 is doing. It's doing the backend.
So does it mean that, as I understand that now, let's say, processor, let's say 12,000, let's say 500, is spending a lot of time waiting, and processor, which is, let's say 0 or let's say 1, is not waiting for receive. So is it a kind of percentage, or it's absolute value?
So keep in mind, this, what you see here is SST backend. So I'm streaming through memory, right?
Okay, it's streaming.
So the one that you most likely would want to see is the BP4, which I think is 50 something,
so it's
right?
streaming. It's just I/O part.
Yeah, exactly.
Okay.
This is the plot which you want to see.
Also,
because the recommendation is going to come back down from me and Stefan, and we're going to most likely recommend the BP4. Because the problem you will have to do is you need to do these checkpoints, right?
Yeah.
And you have to write on the disk at some point.
But is this also ionization? Or
that's correct.
And then this is surprising. So it's an MPI gather.
Yes.
Why the last core should wait for the previous ones? So once more, is it percentage or it's absolute value? It's kind of, so are these numbers, so it means.
That's a good question. I have to check this.
Yeah, because what I'm saying, it can be some relative or exact. So question is, if processor, let's say 12,000, is gathering, so spending less time on gathering than first processor. So can you check this, because
I think we'll
it
check
should
it,
not
because
be the case. I think
check
it's
this.
just I think it's a relative and not absolute.
Okay, I'll check this. Because don't forget, we didn't change anything to code. We just run the code, and we wanted to understand from in terms of MPI communication.
If this is the case, if these are absolute values, then one has to dig. So I have to check why this is happening. Thank you.
Yep. No worries. Any questions?
I have a question. Sorry. If you are doing the profiling, you are doing the profiling on the one threaded or one process application with the gprof, or you are profiling the whole?
Oh yes, that's an excellent question. Yes, I'm profiling. So you have to compile the code. So just like how you do the compilation step, you also have to enable a certain flag, and then I run the code, and it's profiling the entire simulation.
So all the tens of thousands processors.
Everything, yeah.
But thank you.
Yep. Yeah, question?
So you showed some really nice analysis for how the code performs in the raster file system.
Yeah.
Did you have the chance to do the same for other file systems like NFS and ZFS?
Yes, actually, that's an excellent question. So I didn't do this.
Okay.
This is on the raster file system only, because that's the one that's the mostly used. I am also planning to do this on Vega, because Vega has a different file system, and then also the Mare Nostrum as well. I'll also check this.
Okay.
Yeah, but for now, the results here is on Dardel, which is the raster file system. Yeah.
Thank you.
Yep. Oh.
Michael, please go ahead.
Yeah, so maybe a comment on the last question. So if you know Adios and Adios 2, it allows you to optimize for not just certain file systems, but also certain parallel I/O system configurations, independent of how you wrote your code. Maybe that's an important input here at that point.
Yeah, that's good. I forgot about that. Yeah, you're right, Michael. There's many different things we haven't tested, because we just wanted to tick the box for David to help him moving to the next step. But Michael said there's many different things we can do now that we have Adios 2 and OpenBMD. Yeah. Question?
So thank you for the very, very good and informative talk. I just wanted to go back to the part where you said that BIT1 was heavily memory bound.
Yep.
I never expected the particle and cell code to be memory bound. I mean, if anything, particle and cell, I mean, from what I understand, should be like very highly arithmetically intensive. So my question is, what part of the code is actually heavily memory bound? Like what?
So the RJ and the RJ is taking the most time, and it's connected to the binary. So you have the Monte Carlo collision, where functions are happening as well. This is taking a lot of the time. So you have also the solver as well. It's happening as well.
Okay.
Yeah. So it's taking a lot of time. It's because the David's code is special. It's not like the other PIC codes. We actually wrote a paper on this. We had a reviewer ask this question: can you compare why this code is so unique? And then we actually did this, and we compared it with a lot of the very fancy codes, PIC codes. And David's code has a special feature, especially when he's using this Monte Carlo. He's doing a lot of physics, and he's trying to answer a lot of questions. So it's actually doing a lot of work. So the RJ and the mover is what the profiling tools picked up. And then when I ported it, well, I'll tell you tomorrow about the GPU part. When I ported the GPU, it told me something different, because now we're using GPUs, using threads. So now we can use less MPI ranks, right? We don't need to have MPI processors anymore. We can use threads. So it's doing some different things at the end of the day. But David's code is quite advanced, even though it's a 1D code.
Yeah.
Yeah.
Oh,
I think there is a question also from Michael. If you finish.
I had a follow-up.
No, actually, sorry.
Okay. Just you mentioned you were using MPI processes on one node. Is there any reason, like, are you using OpenMP also, or?
Oh, that's tomorrow.
That's tomorrow. Okay.
Yeah, that's tomorrow. Yep. Yep.
So I was right.
That's tomorrow. So today,
Please,
no optimization. We didn't do anything.
Yeah.
Tomorrow it's going to be optimization and GPU porting. Yeah. Question?
So maybe one
Michael,
comment
you got
to
a comment?
Yeah, I have one comment to the arithmetic intensity of PIC codes. I'm not sure who asked this, but actually today's highly accelerated PIC codes, almost all of them are memory bound. If you show me any PIC code that can use more than 20% of the overall flops on a machine, I want to know it. So at least one that's in production.
Yeah.
So the problem here is manifold. First of all, you're actually not doing that many computings with a single particle or a single field quantity. But the second one is that you usually have two domains, particle and fields, that do not have data locality with respect to each other. So that means that particles move along in the grid, and that means that usually you have to somehow take care that you can still do data local operations that involve both particles and fields, which is happening in all the PIC codes, because you have to put forces on particles, you have to compute currents or charges from fields. So the point behind this is because particles are moving inside the grid, you almost always have violation of data locality. And data locality is key in order to enhance throughput in the simulation. So I don't know of any advanced PIC codes that can do more than 20% of the full arithmetic capability of a supercomputer.
Thank you, then, Michael. Yeah, that's totally right. Yep.
Thank you for the presentation, Jeremy. So my question is, you show that changing the IO using EDIOS 2, you got improvements also in the mover function and the RJ function. So my question is, do you call the IO inside those functions? Or if not, why do you get improvements?
So what is the question? Do I code the...
Do you call the IO through the RJ or the mover functions?
Oh, no, no. So you mean from the, like, for example, Dashan?
No, if you take like the gprof plots, you show that when you change the AO, you gain improvements in the RJ function and the mover. So my question
you mean the parameter in the input file if I'm changing in terms of diagnostics, you mean? Because the IO is related to the diagnostics.
Yeah, indeed. That's why. I mean, you mentioned that you got improvements in the RJ function and the mover only changing the IO part.
Oh, so when I mean by I changed let's go to that plot. I know what you mean. So you mean for 1 second?
Yeah, exactly.
Like for example, this one.
Yeah.
Yeah. So this plot, nothing has changed. So nothing changed in the input file. This is the exact replica of running BIT1. The only difference is it's just EDIOS 2 and OpenPMP enabled. So what you see here is the gprof telling you how much RJ is running in terms of the function, how many call it's doing without doing anything. This information is from the profiling tool. So nothing has changed. Input file,
okay,
nothing.
Okay, because you don't have the elapsed time.
Correct.
Okay.
Yeah, this is totally different. So remember I told you, every tool has a question. So you have to answer, what's the most frequent function? This tells us that.
I think.
Which one is being called in the most at the moment and it's taking a lot of time. So this question you're asking is, I believe you're asking is how fast the IO is being used. So I believe that's.
Maybe this question can be answered if we have the absolute numbers on this graph, because this is relative. So
yeah, so this is not,
I think it's a bit
this is not
confusing.
the actual amount of, how can I say it? This is just telling us how much RJ is being used.
So maybe in the end, there's no improvement.
Okay, no, exactly.
And absolute
That's what I was
values.
wondering.
Yeah, this is not the actual, this is not the actual, put it like this, this is not the actual one that you want to, I would say, optimize. You want to look at, for example, the second one, which tells you straight away the runtime. Yeah. So you have to remember, when you pick a tool, you have to ask yourself a question and you want to answer it.
Another question is,
Yep.
do you have any information regarding the field solver? Like how much time does it take?
I don't
Or
think.
if it is
It should be very fast.
Okay.
It's very fast.
Yeah, I have to check this. Yeah, that's a good question.
Yeah, thanks.
Excellent question. Yeah, we can do that in the back.
It's 1D solver and it's very
Yeah.
optimized. And we compared with
And in most
commercial
cases,
ones, and it was
and in most
orders of
cases,
magnitude faster. So
if the GPROF didn't pick it up, then it means it's really, really fast. Yeah, that's it. Yeah, that's me.
okay, so thank you very much, Jeremy, for nice presentation. Now we come back to physics. Yeah. Yeah. Okay.
Thank you.
Now, just a second. Let me set up. Yeah. When Jeremy mentioned that it's a special code, yes, I mean it's a code is optimized for particle, let's say Monte Carlo part. So, and I will explain why. I hope it's now, yeah, full mode. Now about atomic physics and plasma surface interactions in BIT1. So, a reminder of the geometry of the simulation. So you have a plasma here. Plasma is coming to the wall, and there is a plasma surface interaction starting when its particles are absorbed at the wall. So you have plasma surface interaction modules. You need to have it. Then these plasma particles interact with each other via Coulomb collisions, so you need Coulomb collision operators. And then, of course, when these particles are released from the wall, then you have atomic collisions. So you have you need three different modules. One is responsible for Coulomb collisions, another is atomic collisions, and third is plasma surface interactions. And want to say these are not very simple operators, because in one case, when I have 18 species, charged species, in reality, you have 171 collision types. So we have had 171 Coulomb collision cases, and code is handling these without any problem. Of course, it takes longer, but it's not limited. So when you come to atomic collisions, you have 80 types of collision. Types means for instance, electron collides with deuterium, it's one type, but in reality, for each collision type, you have different possible channels. The number of channels are, I say it should be few, this is a type, it's a few thousand of possible channels per collision type. So effectively, in reality, few millions. I will come to this point. And you have up to 30 types of surface target interactions. And most importantly, this is not limited. That's what we need. Implementation of new cases are relatively straightforward. The main problem in Monte Carlo simulation is not routines. Main problem is to get data. So it's not related to my talk today. So motivation for Coulomb collisions. So classical particle in cell simulates only macro fields and neglects particle collisions. So if you now consider distance inside grid, so if we consider one-dimensional plasma, the interaction is constant. The force is between two particles is constant. If you go to 2D, it's 1 over r, and if you go to 3D, 1 over r square. Now, if you go to PIC simulations, you know that because particle cannot force cannot act with some force on itself. So this force should be in the correct particle in cell. This decreases toward the zero. So it means that actually it has some correct value at some distance. So let's say one at the edge of the grid size, but it's zero. It's linear. It decreases for, let's say, linear weighting. At least it decreases to zero for the position of the particle. So if there is another particle at this point, there is zero interaction. So of course it's not correct. And then so you need to simulate also, in order to properly simulate collision, also high density, relative low temperature plasma, you need to have a separate module, which is collision operators. And I remember when at the beginning of my career, the classical PIC code does not have this operator. So we were searching quite long and we found quite a number of approaches. The first one is so-called linear model. So you assume that you have Maxwell distributed particles. So having this assumption, you can calculate Chandrasekhar coefficients. In other words, you can assume that your change in velocity is due to friction force plus diffusion in the velocity space. Proper diffusion is not anomalous or a numerical one. When you have diffusion coefficient in the perpendicular direction, diffusion coefficient in the parallel direction, and these are random numbers, so multiplied by unit vectors in the perpendicular and parallel direction. So in the linear model, these values are pre-calculated and it is relatively fast and it works, but the problem is this is correct only when you have Maxwell distributed particles, and this is not the case. Otherwise we can use fluid approach. Now there is another point. There were attempts made quite, let's say, 90s. There was attempts made to spread this to nonlinear model. So you assume that now these distributions are given. So you calculate this diffusion coefficient from the actual distribution functions, but this was also not so effective because you need extremely large number of particles to obtain proper diffusion coefficients, and this direction was stopped. And finally, we had a binary collision model, which is just same as for any other collision approach. So, I mean, the Monte Carlo approach. So you choose colliding particle pairs and colliding particles. So this is very accurate here. I'm give you very old simulation, so test simulation when we implemented this approach to BIT1. So this is analytic. So this is equilibration of two temperature plasma for analytic, and the red one is analytic and the blue one is particle in cell. And you see it ideally follows this analytic approach. It works. It was introduced by Takizuka-san, so it's 70s, and it's a very advanced one. So the idea is following. So you have particles. Usually in PIC simulation, particles are you have a grid cells which are of the size of grid cells of the size of lambda dBi, and you have to account mainly particles in lambda dBi because otherwise they are screened. So what you do is you collide particles inside grid cells, assuming that it's somehow near to colliding particles inside the lambda dBi area. So what you do is, so Takizuka's model is you have a particles in this grid cell and you just find randomly pairs. So this particle comes here, this particle comes here. So for each particle you have a corresponding pair. So there is also a case when you have one more particle. So it's this very high accurate approach. Takizuka-san and Abe made it also assumption for that case. This is case when you have two separate, actually it does not matter. You can have in this case, we assume that you have same self-collisions, but you can do also collisions with different particle species, assuming that they have different number of particles of different species. But also here you can a very simple approach, and you can do so some particles which you have less particles can collide 2 times, and so each time you find a collision partner. And then when you have collision partner, then you switch on the let's say matrix. So you know how the scattering angle is distributed. It's a, let's say, Gaussian distribution. You know what is the average width, can be calculated. We can follow this exactly analytically derived. And having this probability function, then it's trivial to calculate this, or what will be after collision velocity. This is a relative velocity, what will be after collision velocity. The difference of BIT1 is more, I call it more advanced for me at least, but we had some discussion with Tagizuka-san. So what we do is, in my case, you do not sort it. I assume that it's 2 time consuming. What I do, I just randomly choose particles. So you know how many particles have to be collided, and you choose so many pairs. It does include possibilities that you have also one particle can collide 2 times, and some particles will not collide this collision time step, but in average, so if you have many time steps, all particles collide. I think this is more natural probability approach, because this assumes that in average we have so many particles, and not necessarily each time step each particle. And it's faster, this was advantage. Anyway, this is quite good approach. It's really all the possible, let's say, relaxation times we are checked by me and by others. We also implemented this in the SPICE 2 and 3 codes, and the same. Now coming to BIT1, so how this is treated. It's much more complex than you can imagine, because we are using this code for different tests, and sometimes you get very interesting results, and we don't know what are the reasons. So sometimes we have to even switch off some kind of collisions, even say that, okay, in this area there are no collisions. So, and the input file looks like this. So Coulomb collision means this parameter means how many so the flag. So if it's 0, it means it's no Coulomb collisions, and then if you have 3, then it means that 3 particle species, first 3 particle species are colliding. It means it's self collisions plus collision with each of these 3 possibilities. Yeah. Off CC means sometimes for instance, you wrote, let's say, electrons, deuterium, tritium, and then neon, and you, due to some reason, you don't want to consider electron collisions, you don't want to change input file, you tell, okay, these particles will not collide. Yeah. So electrons will not collide. So, and then you put this one. Now, second is, if you are interested to include collisions in some area, but exclude some area. So this was done when I was investigating collisional sheaves. I wanted to know, okay, are Coulomb collisions responsible for new effects? And so I was telling, okay, in the upstream plasma, there are Coulomb collisions, but in downstream, so near the sheaves, off. So this is a flag for this. These are, so the flags specifying, so if it's on, then you are specifying distance from inner diverter, so from 0 to this point, you have a case without area, without Coulomb collisions, and same in the outer midplane. Then you have average density, because this is only used for Landau logarithm calculation. Actually, code is not very sensitive because it contains density in logarithm. In principle, if someone don't want to put it, one can really go inside code and just calculate local density and obtain this. But anyway, it's not so sensitive. CC coefficient is, sometimes you want to say, okay, I want to test what will happen. I don't want to change system. Just I say, let's artificially increase Coulomb collision these strengths to see if is this, so for testing. And you have CC step, because the code has a very refined time step. In this case, can be 10 to minus 13. You don't need each time step to have Coulomb collisions because it's very expensive. So what you do, I mean, just subcycle after 100 steps. So only after 100 time steps, it will make Coulomb collisions, and it speeds up very strongly simulations. Yeah. Then comes specification of the species when you without Coulomb collision. So we say you specify, I think, one or two. I even don't remember. I have to. So I think these are giving which species do not suffer Coulomb collisions, as I say, and then also next is which species do not suffer Coulomb collisions in the no sheath region, no collision sheath region. Yeah. Now these were Coulomb collisions. Now the idea was, when we did these Coulomb collisions, actually we wanted to, when we are working on this scheme, we wanted to find the fastest, I wanted to find fastest sorting schemes, because sorting schemes, we need to know which particles are in given cell. So, and then I realized that it's better to simply carry index of the cell. So each time code knows which particles in this cell are in this cell. So it means that particle actually saved not, so n particle, all times the array has this index I, which shows in which cell it is located. So it means that whenever you want to collide particles, you already know these are particles in the sitting given with given index I. But in a surprise way, this gave huge advantage also for case without collisions, and even up to 5 times speed up the code because of cache hit. So why this happened? Because, and it was good surprise, yeah, positive surprise, because now if you have neighboring particles in the space, you can put these particles as the neighbors in the memory. So it means that when you are calling particle I, so from the cell I, n1 and n+1 and n, so they are using the same electric field, the same magnetic fields, and which is already in cache. So you don't need to, so outside cache, so this cache hit increases very significantly. So it speeds up simulation very, very strongly. There is second point, because it's not necessary to this sorting, but it simplifies to consider statistically independent cells, because each cell is absolutely separate. It has its own particles, so and you don't need to generate large number of random numbers, because you generate for one cell with largest number of particles random numbers, and you can use this random number for the other cells, and it also speeds up simulation very strongly. Massive parallelization was straightforward, because you already know when particles are leaving the cell or where particles are leaving. If it's a domain decomposition, you know when particles are leaving the given core. So it was no very small step to go to real parallelization. And most important part, which is coming and which is specialty of BIT1, its particle trajectories are calculated with the same accuracy at each point. Why it's important? Because now if you go to large system with very fine resolution, we have a problem. So large system means we have a large system like tokamak Sharapov layer can be 10 meters. I mean, in reality can be more, but let's say 10 meters. Your grid cell can be very small. Let's say, I don't know, in this case, grid cell can be, I don't know, let's say 10 to minus 6. And your time step multiplied by velocity is smaller than this value. So in the classical model, so you have a large number, this x can be near to 10. So you have 10, so new position is calculated from old position, which is of the order of 10 meters. But this value, and you have parameters here, you can have practically 10 to minus 10 times smaller than this value. So you are adding, in the best case, you are just reducing accuracy. So you have only 4 digits to improve your position on the right. So when x is large, and you have second order accuracy if your starting point is near 0. So if you in the left and right, you have in asymmetry of the accuracy, and this of course unacceptable for large simulations where accuracy is the main point. You get a numerical hitting and so, or inaccurate simulations. What's happening in BIT1? BIT1 is optimized for each cell. So BIT1 knows, because you have an index where a particle is sitting, and the maximum size of this parameter is 1. It's normalized. So it does not care if you are at the starting of the system, so when this at the zero, actual distance is near zero, or if it's a 200 meters, because 200 meters will be 200 cell plus this small distance, and the accuracy is same. And this keeps very high accuracy of the simulation, which is necessary for large systems with high accuracy simulations. Now, coming back to collisions. So we consider Coulomb collisions, then we have to consider also the atomic collisions. And these collisions are also treated with Monte Carlo. The principle is same. So what you have is you have a probability of collision. You having this probability when you have the collision frequency defined as given here, so density of target particles, relative velocity, and the collision cross-section, which depends on the velocity. So if you decides to have a collision, then it comes to just updating of the velocities after from before to after collision velocity. So, and if it's an elastic collision, you can have many channels of the transitions. So, but there are different ways how to decide when collision appears. So direct simulation Monte Carlo, it just calculates average time between collisions based, so it inverts this number, so this is random number from 0 to 1, and then you calculate time for collision for given particle, and then you collide this particle after collision time. It's good, but it's very time consuming because you have to know additional parameter for each particle. Much better model is a null collision method when you calculate the minimum time for collisions. And you know that you have to consider collisionality of particle after these time steps. So, and it's faster because you don't need to have for each particle this additional parameter. You have to keep that whenever this particle, when counting is starting after this time, you have to analyze particle for collisionality, and it's much faster than direct simulation method. But also here, it's still, we didn't like this because we have to still keep particle and measure their collisionality much faster, because if you have a large number of particles, so if you have 10 to, I don't know, 13, you have to still analyze so many times. Much more effective approach, which was developed by probably me. This non-counter-based model for nonlinear collisions. Actually, XPDB1 had a linear model when you are colliding particles with some background particles, but I generalize it for nonlinear case. And its idea is you are analyzing some area, looking in this area, how many collisions we have in this area. More importantly, you don't need to consider whole number of particles. What you can say that I consider maximum particles which can be collided in this area. So you don't need to analyze all particles. You analyze just this number of possible collisions, and it does not mean that particles have to be necessarily collided. You have to just analyze these particles, which are usually much smaller than total number of particles in given area. You just, if you find out that these particles from this number have to be collided, you switch on collisions. And so this step is same in all collisions, all Monte Carlo approach. So I cannot guarantee, probably there are much faster methods, improvements for null collision method, but we were quite happy with this and it works quite well. Yeah. So what kind of collisions we have in BIT1, and all possibilities which we can have, which are important for the fusion-related applications. So we have, so on the left-hand side, you have number of colliding particles, and the right, you have number of product particles. So 2 is common, so elastic collisions or charge exchange, and so on. So we have a recombination, so two particles collide. It's a radiative recombination, so ion collides with electron and it's recombined. So we have atom coming out. Yeah, you have dissociation. So for instance, electron collides with molecule and dissociates. So you have electron and two atoms coming out. You have two particles, colliding, and four particles going out. So after collision particles, this can be double ionization. or dissociated ionization, it's given here. So electron collides with D2 molecule, and you have, let's say, double, so dissociation with ionization, which have 2 electrons, 1 d atom, 1 d plus ion. Yeah, and you have also the 3-body recombination, which is very important for fusion applications for low-density diverter plasma. So you collide, so D plus collides with 2 electrons, and it's recombines one of the electron recombines with ion, and you get the deuterium atom and electron. And this was very complex to implement because there were no corresponding cross sections. So I had to start digging in the atomic physics, and so we derived corresponding 3-body collision cross section. Now about cross sections, this is the main headache. Getting atomic data is most difficult, especially you never get accuracy which you want, because if you consider one of these collisions, you have 6 times differential cross sections because it depends initial energy of particles, energy of first product, energy of second product, energy of third product, angular distribution of these particles. Of course, you never get in reality. In some cases, we had triply differential cross sections. It was maximum, but still, in principle, code can treat all existing ones, but in reality, it's just a multiplication of different simplified approach because there is no data. Although code can treat any approach, data with any accuracy. Yeah? Now, how the input file works. So we have, this is coming from the input file. So we have first parameter which specifies ions. So how many particles are colliding. Then comes second, how many neutrals we have collided. So in reality, this is not a, there are no ions and neutrals. You just assume that some particle group belongs to primary particle for collision, another group to secondary, just to not to mix particles. And so in this case, we have 2 particles primary, so it can be electrons and ions. And now we have 2 second particles for these electrons. And then you have to repeat this line for each collision type. So first, now these parameters define colliding particles, first and second particle. Even for, let's say, 3-body recombination, then this defines the 2 electrons or 2 first particles because it code knows that it's 3-body recombination, so first particles should be taken from here. This defines collision type. 0 in this case means electron collision with deuterium hydrogen isotopes. This defines what are the, and now the rest defines the outcoming particles. So I means ionization. So if you have an ionization event, these are the ionization of first and second particles, because it's general. It does not necessarily should not be necessarily electrons, can be any other particles, and second should be, for instance, if you have a let's say deuterium atom collides with electron, first should be electron, second will be deuterium ion. FE, it's effective ionization, which I will speak. It's a dress cross-section method, which I'll consider in the next slide. Then we have different cases for recombination because, and also it can be for the asymmetric charge exchange. For instance, 2 particles collide and you have 2 absolutely different particles. You have to specify what are the outcoming particles. Then we have a case with 3 outcoming particles. So it can be, for instance, dissociation. So you have and then you have dissociation with ionization, and you have to specify on 2 particles because in this case, you know what are the 2 first particles. It should be same electrons, and so that's enough. Now, SEC RR, and these are, let's say, 3-body recombination parameters. This is specifies which particle you have after a 3-body recombination. And this specifies kind of accuracy of your calculation because, in principle, you can have generated atom in different quantum level, and this defines how many quantum levels to take into account. But more importantly, if you specify 1, it switches to dressed cross-section method, which I'll describe below, which is much more accurate and takes multi-million interactions into account. Now, what does it mean, dressed cross-section method? Very briefly, if you consider collision between two particles in classical, let's say, kinetic codes, majority of kinetic codes maybe even neglect this type of collisions, but if they are given in a trivial approach. So it's a coronal approximation. So two particles. So if you have a ionization, electron collides with some particle and ionizes or not. That's all. So if it's not ionized, you are forgetting this. Or if it's excites, you forget about this. So you assume that there is no collision. So particles are de-excite or come to the ground state in time before second possible collision arises. In reality, this is not correct because you have a high density plasma. Before particle de-excites, you have second collision. So you can have a first collision excites atom and second collision ionizes. And if you go to high density plasma, these type of collisions are ionization collisions, much more probable than these collisions. And you have to take them into account. And you can see these are profiles. So it's an inner diverter. So inner wall, let's call it, for different cases. So you have a most dense case. This is eta. You have jet, existing machine, and our machine, it was compass. And you can see that with increasing size of machine, this density at the diverter region can exceed 10 to 21. So this means this kind of interaction, so multi-step ionization and also multi-step recombination becomes very important. These are corresponding densities, and these are these effective ionization rates depending on the different density as a temperature, of course. So if you consider low densities, there is no big difference. I mean, there is, let's say, for different temperature, this is, let's say, it's a relative rate, so relative to classical coronal approximation. So for low densities, there is no difference. But whenever you increase the densities, let's say 2 times 10 to 21, which we have it for eta, the difference for low temperatures, and we are in this range for eta, so it means that you are increasing almost more than 1 order of magnitude your ionization rate. So it means you have to take this into account, yeah. And how it's done, and this was most time consuming and hard work for me, because initially I said, okay, we have massively parallel code, we can follow any excited state. But when you come atomic data, you understand that it's impossible to do, because you can do it for, let's say, there are some codes from jets, so you can treat 30 atomic states. And these 30 atomic states are still okay. You can consider, because you have 930 transitions, it's okay, you can follow 30 states. But now whenever you go, and this is main plasma, so it's deuterium part, but whenever I go to impurities, which we have and we have to have, so they are neon impurities, and you see how many states you have to consider for H plasma. So you see that for neon, you have to consider 89 excited states, and if you go to neon 4 and so on. So in general, even if you assume that you want to consider only 4 times ionized states, you are 500,000. If you continue this, you are all of the order of 1 million and even more, just for neon. So it means that we cannot do it directly. So too many processes, yeah. One possibility was to consider bundling. This is done for tungsten. So tungsten is high Z material, and there are examples you assume, okay, neon and neon plus, we assume it's a 1 particle species, and neon 2 and neon 3, or in this case, ionized states of tungsten are bundled. So ionized states from 2 to 7 are called 1 particle with average charge and so, but this is not okay, because you can't do it interpretive modeling. So it means that you can compare with experiment. You can say, okay, for this experiment, this was good assumption, but whenever you want to do predictive modeling, this does not work. So you really need to know what's happening for each ionized states. And then I introduced a dressed cross-section method, which is following. It's very simple. Idea is very simple. So we have the cross-section from atomic physics, and we have rate coefficients obtained from collisional radiative model, which takes in account multi-million transitions. I say, okay, let's unify these two. So rate coefficient, which depends on density of plasma and temperature, and kinetic model, and you unify these together. So, and we derive a, let's say, temperature-dependent, energy-dependent, and density-dependent cross-section, which has proper limits. So if you go to low density, this R goes to any near 0, and this goes to 1. So you recover your cross-section for low density plasma. If you go opposite now, if you go to, let's say, Maxwellian plasma, very high density plasma, then, when we average this, integrate this cross-section of a given distribution function for Maxwellian, this cancels, so this will be with Maxwellian, so convolution gives rate coefficients, this one, and this cancels, and you get the integral of this value gives the proper rate coefficient. And that these two cases are described here, so these two conditions. So it means that you have your proper scaling, and it's a kind of in between full kinetic treatment and, let's say, poor coronal approximation. So advantage that number of collision channels are effectively, very large numbers can be effectively incorporated, and the rate coefficients contrary cross-sections are known, so whenever you have cross-sections, it's much easier to find corresponding rate coefficients. Of course, it has disadvantages because it needs calculation of temperature and density each time step. This is okay, it's just time spent from simulations. And one has to know also, okay, let me skip because one has to know also the threshold energies is not so easy to calculate. And most importantly, the main limitation that distribution, you have to assume that they are near Maxwellian. But anyway, you need this for high density plasma, and then this assumption works. So this is can be applied to ionization as well as to recombination. And I think I do not have much time. Let me very shortly say about the plasma surface interactions. So in the code, you have possibility to treat plasma surface interaction in a linear approximation. Linear means that you do not consider interactions inside the surface. So what you have is if particle hits the wall, it can, let's say, scatter, or it can inject some secondary particles. So you have actually two initial parameters, energy and angle of incidence, and then you have particles which are coming with some given energy and angles. So in principle, your rate coefficients for sputtering or recycling is quite complex function. In this case, it contains, if you consider only two particles, 3 is too much, you have to additionally two additional parameters, but let's consider those two particles, red and green. So you have initial data, incoming energies, and then outcoming energies at angles. Of course, it's very difficult to find such data. They exist now. So what you can find, either data correlated between energies of these two particles. For instance, when you have a recycling on plasma, so if deuterium atom hits the wall, then there is a correlation if you get out deuterium molecule or deuterium atom, and though you can have this correlated probability of, let's say, sputtering or the recycling rate. So it depends on the energy of initial particles and energy of outcoming particles. In most of cases, it's just simply multiplication of separate particle emission probability. So it means that if you have a probability of emit set for recycle, for the reflection, it's a reflection coefficient. And if you have some recycling, so you have a recycling coefficient for this, and you assume there is no correlation between them. This is the main assumption. And the Monte Carlo is done very simple. You calculate this probability from the given data and then compare to a random number if it's larger than gamma is larger than random number, you just emit particles. Very shortly, how this is done in the code. So this is done for each particle species. So what you have a number of secondary particles you can emit. Up to now, you can have up to 3 different particles to be emitted, 3 different species of particles. If you want to change it, you can easily update in the header file. So it's H file. Its limitation can be removed. I never had a case when you needed more than 3 emitted particles. These are first and second emitted particles. Actually, you can separately you can repeat this line many times, so you don't need to put second separate particles, and this is done only for cases when these collisions or the emissions are correlated. As I say, if you have a recycling of deuterium molecules and atoms, they are correlated, so you consider as a one event, and then you put it here. Then comes a type of secondary particle or emission type. Then sometimes you need to put, in this case, is probably secondary. This type means you just consider constant emission, sputtering rate. So 1 means any particle which coming is definitely emitted back. So is a different particles in general. L and R all times means left and right wall. And these are work functions. These are energies of emitted particle. And these are types of particle emissions. You have to check these parameters exactly in the BIT1 manual. And then also we have the secondary particle, the surface, temperature. So this defines, in some cases, for instance, for tungsten, this defines your temperature of tungsten particles. So all of this can be repeated for multiple times. There is no limitation. You can put 100 of secondary particle emissions here. The only point that you do not put, the main limitation that only 2 particles can be correlated, emission of 2 particles pieces can be correlated. And for this, I suggest go to manual. And with this, I've complete all Monte Carlo description of BIT1. Thank you for your attention. So if you have questions, please ask. Otherwise, we can discuss. Yes, please. But please at the microphone.
You have, let's say, 3 or even more particles involved in collisions. I would assume that it is not trivial to assure the momentum conservation. Is this done?
Yes, it's absolutely done. Momentum energy, unfortunately, PIC codes are very sensitive to energy conservation. It's absolutely conserved, yeah. It's done in a following way. So suppose we have Coulomb collisions. Then we have 3 species, let's say. Neon, single ionized neon, deuterium plus, and electron. So first, it's doing self-collisions, electron with electron, deuterium with deuterium, then neon with neon. Then it's going electron to deuterium, then electron to neon, and then deuterium with neon. And each collision type conserves the energy. So in the same operator, so to ensure true probability, the sequence is changed sometimes. So sometimes you can go for different sequence, or maybe so I don't remember. Probably it's each sequence can. So electron first collide with neon, and so on and so on and so on. But each collision event, independently of which particles are colliding, energy is conserved. The only problem is here, which I already discussed yesterday, particles have to have same weight. This is very, let's say, strong limitation. There are some models, but they are not okay. We can do it. We want to do it when time comes. We have ideas how to do it properly. But it's the main point, how to treat particles with different weight, yeah. Yeah, please.
So I have a bit of a question about in the Coulomb collisions. You don't include the actual simulation density in the calculation of the Landau logarithm. like, have you tested the difference that it makes if you did not consistently generate?
Yeah, it's zero. It's
zero.
It's only Landau. I mean,
yeah.
Density, of course, is calculated because the Coulomb collision strongly depends on it's proportional to the probability of collision proportional to density. But Landau logarithm, it contains density in a logarithmic way. So if you go to if you have a one order, so if you put 10 to 20, and your plasma is one order different, the difference will be 1 point something, so 3 and so. So it's not so crucial. And once more, actually, it uses very complex. So it chooses quite whenever you specify collision type, it automatically chooses the proper Landau logarithm, or let's say it's not Landau, it's Coulomb logarithm, probably its proper name. And then it's quite extensive calculation. So for instance, electron ion is 1, for electron is second, for ion is different. To be honest, I mean, these are still approximations, so you don't know which one is correct, because anyway, when you are calculating Coulomb collisions, you are artificially adding these limits. And I think within this error, our approach is that. But once more, if someone wants, it's trivial to density is anyway calculated, you can put this. The idea was that you don't. The idea is we are trying to reduce possible floating operations to the minimum. So if you calculate Landau logarithm at the beginning, you don't need to calculate for each density separately. So you can do it. It's quite simple. It's one line in the code, but then you are additionally have to add multiplication for each cell, which I wanted to avoid, I think, but it can be easily done. I think Michael wants to add. Yes, please, Michael.
Yeah, I have a question to David. First of all, wonderful talk. Thank you very much. My very first question is, you showed that you actually have very, very many reaction channels with very many possibilities of combinations. Even if you're not going through the full rates, you still have a lot of different probable channels that you're going through. So my question is on your experience with having enough statistics for all these channels in the simulations. Yeah. So how do you deal with that? How do you ensure that you do not need a million particles basically to cover all of that?
Yeah, I mean, no, I can tell you, I made these tests really long time when I started these implementation operators. I think sufficient statistics was when you have 100 particles per cell. Already it was okay. That's a very good. Unfortunately, in some cases, this is not the case. For instance, if you have tungsten particles, I mean, plasma density can be 10 to 22 for eta, for instance, or more than 10 to 1, and tungsten concentration, it can be 10 to minus 5. So, of course, if you have in one grid, you do not have 1 million particles. So, I mean, because it's the same weight. So it means that you can easily have few, let's say 3, 4 tungsten particles, and then statistics is not so good, but we don't know how to do. The idea for such cases, we have to kind of separate weights, but already for 100 particles for Coulomb collisions, it's absolutely enough. So it's a very accuracy was of the order of few percent. So, and I mean, and most important, you can increase it. You just put more particles, you use more cores, and then you can control this accuracy. Yeah.
And another question on your dressed model. So you already said that one of the limitations is that you have to assume near mixed value distributions. Have you looked at other distributions, actually? I mean, in your case, probably not anything relativistic, but in principle, you could do similar things and maybe do a small adaptation towards different distribution functions.
Yeah, it's a good question. I mean, the problem is data, available data.
Yeah.
So yes, of course you can do it. I mean, whenever you do this implementation, in our case, when we update code, we keep this possibility to update it further without big efforts. It means if someone provides us with corresponding rates for non-Maxwellian plasma, we easily can be implemented. It's just trivial, so probably it's just a table or function, and it can do any. The problem is this data doesn't exist.
Yeah.
So when I derived, we are plasma physicists, so it was for me, I was afraid to apply this, so I went to the atomic physics conferences where there are just atomic specialists. I presented it there, and it was good. So it was stamped that it's good invention, and so they said it's perfect, nice, and that's I'm applying for this. So it means that if someone provides us with this R for the other distribution, I mean, code is ready, and the general model is not necessary for BIT1, but general model exists. So it's trivial. You just take another rate coefficient for that model, yeah. So if it's relativistic, you can use for relativistic too. So that means that you have to consider relativistic cross-section, corresponding rate coefficients for zero density. So it means it's just an integral of this cross-section and corresponding relativistic rate coefficient. But one has to take into account that these rate coefficients can take multi-million channels into account. So this is collisional radiative model outcome.
Mm-hmm.
Not done by us, this is done by atomic data providers.
Yeah. So we have to keep the NIST database alive no matter what.
Yes. Yeah. This is big problem. I'm not joking. Main problem is advances is just. I went about 20 years ago to Strathclyde. If someone knows ADAS data, so we and others people did not. They are surprised when I ask this question. So can you provide me with cross sections? And they say no. We do not keep it. We have rate coefficients because everyone was asking rate coefficients. Although you need to calculate cross sections before coming to rates, but due to limitations of the memory, they never kept it, and they don't want to repeat this. So it's really so you can have more rate coefficients than cross sections. Yeah, it's surprising. Yeah.
Okay. Thank you very much, David.
Welcome. Please go. Okay, good. Yeah. Okay, so I think that's all. I think we did quite more than we planned. So we have to probably move for lunch because another conference people comes in half an hour. So thank you very much. So yeah.